Okay, a couple things. Today we are going to be working on learning about colligative properties and molality, and then we're going to go back into lab. Before we go back into lab, I'm going to show you what I see as far as what's going on with your Learn Smarts.
Oh my.
18 students have not started Chapter 8. If you are behind, you need to jump right into Chapter 8, work on Chapter 8 so that your Chapter 8 test will be good. And then you can go back and do the others when you can to get caught up for the final test of the end of the year. But if you do not, okay, I'm really, guys, you've got to do your Learn Smarts. You've got to do your homework. It's 20% of your grade. You got to do it. Okay, if you don't do it, you're not going to get a good grade. Okay, and if you don't do the Learn Smarts, you don't do the homework, you're going to suck on the test. So you've got to do it. Please remember that on the middle of the board up there in purple are the days and times I'm going to be here after school. Please come get help. Please come during tutorial. Please come before school. I don't know what else to do for you. Okay, if you don't come get help, I cannot help you. So please, if you are not in Chapter 8, you need to start it today. Even if you haven't done 6 and 7, and 6 and 7 are still open, you jump to Chapter 8. You start doing the Learn Smarts. You start doing the homework for Chapter 8. You need to have them done before the test. Okay, before the test. They're not going to help you after the test. Okay? All right, now I'm going to get off my soapbox and we're going to go into lecture. So grab out your lecture notes, even if you haven't finished your pre-lab. And then I'll be letting you back in lab as you get your pre-lab done. So you're going to go over colligative properties today. We started with concentrations last time. Parts per million, %. Those were pretty easy. How many understood last time's lecture? Okay, hopefully you were able to get it. If you weren't, you need to be coming in tonight. Okay? At least till 3:30, and then you go walk, and I'll be back at 4. So if you want to stay during that period, then you'll be gone and come back. I'll stay as long as you need. Okay? Tonight after school, I'll be here till 3:30, and I'm going to go walk from 3 to 4. You're welcome to stay in class, and then I'll come back at 4 if you want my help. Okay? All right. So colligative properties. There's 4 of them. Okay? They depend on the concentration of the solid. Solid is the thing that what? That's the one that's being dissolved. Okay, the number of particles of solid affects the properties of the colligative properties. The identity of the solution does not. That's really important. The identity does not matter. But the number of particles does. The number of particles does. This is what the colligative properties are. Boiling point, elevation, freezing point, depression. Osmosis is possible. There should be one more. My brain's not. There's only 3 right now. Those 4. Okay, so really quickly. Hey, what are the colligative properties? They are properties of solution. Boiling point, elevation. So we think boiling point, it's going to higher the boiling point. Yes, sir.
Where's the...
If I have any more, they're over there. If not, you'll just have to take notes on your own. I'm not sure if I have any more, but if I do, they'd be in that other in the top covered. Okay, boiling point elevation, freezing point depression, and vapor pressure lowering. And osmosis is possible. So, boiling point elevation, that means my boiling point's going to go up. Freezing point depression, my freezing point's going to go down. Vapor pressure lowering, that amount of gas above a liquid is lower because it doesn't want to come out of solution. Osmosis is possible. That's part of the lab we're going to be doing today, where we use dialysis tubing, and we're going to be able to see what passes through the dialysis tubing. Okay? So those are the 4 colligative properties. You need to know those 4 colligative properties. We're actually going to be using osmosis is possible today, but we're going to be doing boiling point and freezing points too. Okay? Osmosis, pressure lowering has to do with Pervner. The only difference is, so you're going to just have to take notes, sorry. The only difference is we do it as PV equals nRT. But what they do is they combine volume and moles, so it becomes N divided by V equals RT. They call that, so they make that right there is molarity, right? So then they rearrange it and say P equals molarity times R times T. And then they say that pressure is specific because it's osmotic pressure. They use a capital pi. That's not a very good capital pi. Basically looks like a tabletop, a capital pi. That's osmotic pressure, okay? So when we do osmosis as possible, when we're talking about vapor pressure, we're using Hermner, but they just rearranged it and put this as molarity, moles over volume, okay? So again, Hermner's coming back to haunt us a little bit, okay? We'll go more into it again. Okay, so going forward, maybe, oh, that was wonderful. Okay, so boiling point elevation, freezing point depression. You can think of it like an alligator. Boiling point is going to go up, freezing point is going to go down. This equation is basically the same on both sides. The only difference is that you're changing the K. The K changes. Okay? The M here is also not molarity. It's molality. Okay, wait a minute. You tell me I got molarity, and that's moles per liter. Now I got molality. So remember I told you that molarity looked like a mountain to me with a lake in between? So I could remember capital M, moles over liters. Well, molality is like this fat little roly-poly thing. Okay? So I think molality. I overemphasize because I want to remember what it is. So it is moles per kilogram. So molality has to do with weight. Molality is moles per kilogram. Okay? So I'm putting molality into this equation. We use molality a lot in industry because it's easier to weigh something than it is to measure the volume. I can roll a dump truck of chemical onto a scale, I weigh it, I roll it off, I know how much is in there when the empty dump truck comes back. Yes?
So what is all those things in that equation?
Okay, they're right here. So this is for freezing point, this is what you're going to need to have in your notes, on your card, whatever. The negative 1.86. That's going to tell you how far it's going to go down. Okay? Take a note. Okay. This one right here, for boiling point elevation, it doesn't elevate it quite as much as it depresses it. So the boiling point constant is 0.51 degrees Celsius per mole. And we would add that because we're going to elevate boiling point. Freezing point, we're going to take it away. That's why the negative. So we're taking it away from 0. Okay? All right. What that does is it shifts what we were originally. So this is our pure solvent phase diagram, and you see what happens when we add a solid to it. It widens the Y. Okay? It widens the Y. It lowers the freezing point, lowers the freezing point and increases the boiling point. Okay, everybody got this down, because this is going to be equations you're going to be using. So, on my card, I'm talking about my card, the things I would put on my card. A generic, delta T equals KMI. I would also put KF is this for water, KB is this. Now that I, what is that I? That's how many parts will it break into. Okay, so if it's covalently bound, if it's sugar, it's not going to break apart. It's going to solvate, but it's not going to break apart. So it's one particle. If I put salt in, salt's going to break apart to Na and Cl. And then it's going to solvate. So I have twice as much just with NaCl. So the I for NaCl is 2. The I for sugar is 1. Okay? So it's how many parts will it break into. Okay? All right, going forward. Whoa. So if we look at this, this is everything that you can use as a solid, or solvent, has its own K value. It has its own melting point, it has its own boiling point, has its freezing point. Each one would be used as a K. She sticks pretty much to water. So as long as you can do water, you're great. If she gives you a different substance, And I've got to look and make sure she doesn't. But if she does, then instead of adding it to 100, like for water, you would add it to 80.1 for benzene. Or you would subtract it from 5.5 for the freezing point. Okay? So that's where those come into play. Okay. Van Hoff factor I already sort of talked about. That's how many particles it breaks into. So because Na splits into Na plus and Cl minus, I get 1, 2 particles. Okay, so if I'm looking down here, K2SO4, I get 2 K plus ions and 1 SO4, 2 minus ions. So I have 2 here, 1 here, total of 3. So polyatomics still stay as 1 when they break apart. Okay, so what about MgSO4? How many going to get for that? How many for MgSO4? Mg would be 1 and SO4 would be 1, so 2 total, yes.
Why wouldn't it be SO and like since there's 4 oxygen?
Because this is a group that hangs together. It's covalently bound. So any other time you get any of your polyatomics that we have on the back of the periodic table, those are going to be covalently bound. When it's covalently bound, it's 1 particle. Okay? All right, so let's go forward here. Okay, really quickly, let's see if we can do these together. Ready? How many NaCl? How many particles? 2. Good. How many for sodium sulfate? 3. I heard 6 though. There are 2 Na pluses, right?
It's got to be a different.
And now it's not ready. Na plus. That's why my. And there are 1 SO4, 2 minus. So 1 of these, 2 of these, I end up with 3. Okay? All right, what about this next one?
3.
1.
Oh,
This is sugar. That's 1. It's covalently bound. Whenever you see CH and O together, for the most part, it's covalently bound. It's going to be a 1. Doesn't matter what funky thing they give you. Okay?
So does that hold true for ionic bonds?
So, ionic or far apart, that's when you've got to split and find out how many particles it's going to make.
Oh, yeah.
Okay, what about SiO2? I heard 1. Why? It's covalent. Remember on the periodic table, close together, covalent, far apart, ionic. If they're medium, it's polar. So polar is still going to split. So this is 1 particle, so it's going to be 1. What about V2O5? I hear it a lot. You have vanadium at a +5. You have oxygen at a -2. How many vanadiums do you have? 2. How many oxygens do you have? So a total of 7 particles. Okay, because those are not covalently bound. I've got a metal and a non-metal. There's a metal and a non-metal. Not covalently bound, go with the ions. Okay, what about number 6? I heard right, 3. There are 2 coppers and 1 oxygen, giving me 3. Right? What about carbon tetrachloride?
That's 5. Dang it.
Okay, they're both nonmetals. Look at where they are. They're both nonmetals. If they're both nonmetals, it's not going to split. That means, are they above the staircase? Staircase above. Okay, what about barium hydroxide? I heard 3. Is that right? 1 of these, 2 of these. That is 3. Okay, what about the bottom one? 5. Good. 3 and 2 will give me 5. All right, so you should be able to get to eyes very quickly, right? Everybody get eyes? Thumbs up. Know how to get eyes. Anybody thumbs down on eyes? Okay, going forward. Okay, so we're going to do a calculation here. What would be the new boiling point and freezing point? Are you ready? Am I not writing? There we go. Okay, salt water. We got 100 grams of that in that much water. Okay, well, the equation that we had was delta T equals molarity times K times I, right?
What K is that?
KF was negative 1.86 degrees Celsius per molal. Kb was 0.51 degrees Celsius per molal. So those are the things I should have on my card that if she gives me this, I know right away. Okay, they're not something that I pull out of the equation. They're something I have to know. Okay, now the other thing I need to know is molality equals moles per kilogram, right? Moles of solid divided by kilograms of solution. So on the top here, I've got 100 and I've got 500. How much total am I going to have? 600. But I need to get it into kilograms. So if I've got 600 and I need to get it into kilograms, what do I need to do? Divide by 1,000, so I get 0.6 kilograms, right? Everybody okay with that? Okay, next thing we need to do is we need to find moles. Which one am I going to find moles of? Mateo, which one am I going to find moles of? You need to pay attention. Which one am I going to find moles of? Sodium chloride, okay?
Wait, how do we know to find the 25?
Okay, because the top is always the solute. The solute is what's being dissolved.
Oh, okay. That's
Okay? Alright, so I need to find the moles of NaCl. So I know right away, over here I'm going to add up sodium chloride. Looking at the periodic table, I pull this up and I get
Wouldn't it be
Okay.
54?
No, it's
No, 0.54.
no.
No.
You're adding.
Oh, never mind.
Okay, so then we're going to take that 100 grams of sodium chloride and we're going to use our conversion we just found. 1 mole of sodium chloride is 58.44 grams of sodium chloride. Grams of sodium chloride go out. So let me throw that through a calculator. Yes?
So on this, you have molality equals mole, but where's the I? Right.
We haven't talked about the I yet. We're just trying to find molality right yet.
Okay.
Okay, so let's do this. What we get for the moles. 1.71 moles. I'm going to just write it underneath so we have an equation. Everybody agree with that?
Yeah.
Okay, so plugging it up here. 1.71 moles divided by 0.6 kilograms. What do we get?
2.83.
2.83 or 8.5? Okay, and that's NaCl. So we're going to use that later. I'm going to square it so I don't lose it. So we have got this. We've got the case. We need the I. So if I look at NaCl, it's going to split into two parts, Na plus and Cl minus. So my I is 2.
Then we just times by 2.
Okay, now it asks for the new boiling point and the new freezing point. So I have to do two different equations. The same equation, but two different K's, right? So for my new change in temperature of the freezing point, I'm going to take 2.83 molal NaCl, and I'm going to times it by negative 1.86 degrees Celsius per molal, and I'm going to times it by 2. I'm going to get an answer. For TB, change in TB, I'm just going to go 2.83 molal NaCl times by 0.51 degrees Celsius per molal times by 2, and I'm going to get an answer. So get that really quickly.
Negative 10.52 to the top one.
Negative 10.52 degrees. Okay, on the bottom one?
2.88.
Yes, it's
2.88.
2.89. If we're rounding up.
2.89 degrees Celsius. Now, on the top one, since the starting point of water is 0, if we subtract this from 0, it's going to be that, right? So this is my new freezing point. Okay, this is not my new boiling point. Why?
Lower than
Okay, what did I tell you? Boiling point elevation. What's the boiling point of water?
High. Celsius.
100 degrees Celsius. So I have to add those together to get the new boiling point right here. That's my new boiling point.
Is this what we went to the lab?
This is part of the lab, yes.
Wait, what?
This is part of the lab that we're going to be doing. This is how we're going to get to make ice cream.
Ooh.
Okay? So you have to know how to make the freezing point lower in order to make milk freeze, right? Okay? This is not hard. The hardest part was just finding the molality, and then just plug it into the equation, right? Okay? So new boiling point, new freezing point. Okay? All right. We're going to move forward.
Yep.
Okay.
She didn't get all that.
Vapor pressure lowering. Yes, ma'am.
Where did the 2.83 come from?
The 2.83 came from putting right here. That came from up here, my molality. So I used the same molality in both the freezing point change and the boiling point change. Okay? And then when I got my degree right here on my boiling point, I had to add it to 100 to get the new boiling point. Okay? So, third part of colligative properties, vapor pressure lowering. If I have a regular solid, it's going to come to equilibrium. Pretend like this is a cork here. Okay, it's going to come to equilibrium. There's going to be enough gas out in the top and there's so much of it. But if I add a solid here, then my vapor pressure lowers because now my solid is it's absorbing some of the energy that would have allowed some of that liquid to go to gas. So we call it vapor pressure lowering. Remember, osmotic pressure, molarity, RT. Okay?
Wait, is that pi?
It's a capital pi. So,
There's a difference?
yeah. So that's a capital pi. The lowercase pi would look more like a little 10.
Is this
Are there
the same
numbers
number?
different?
Yes, that doesn't have a number. That's just a symbol.
Oh.
Okay?
Oh.
It's just p. In our permanent, it's just p.
Oh.
They just give it, because it's a colligative property, they give it a Greek symbol.
Okay.
Okay? So this is just that equation that I used, where right here we replace n divided by v with molarity. Okay? Just know that it lowers. If I add a solute, it lowers the vapor pressure. We are also going to work with osmosis and dialysis. Anybody know what that word means?
On the same concentration of solution as inside the milk.
Same concentration. So when we put stuff into our body, especially in the medical community, they want to make sure that the saline is isotonic with what is in our body. Because if not, it can cause our red blood cells to do bad things. Okay?
Kaboom.
This is what weight to volume NaCl solution should be made up to be the same as our body. This is if the person needs sugar or is being fed intravenously, that's a glucose solution that needs to be made up in order for the body not to have an adverse reaction. Okay, so those are two that you need to know.
Ah.
Okay, yes.
So if you were to take like a drop of blood and stuff, take a drop of blood, put it in salt water, do you think that blood would kind
Let me show you what's going to happen. We're going to talk about it. Okay, hypotonic. We need to know these words. Hypo means what? Below. So it has a lower osmotic pressure than the body fluid. So if you put something in that's hypotonic to the body, the concentration of particles outside the cell is lower than the concentration inside the cell. Water diffuses into the cell. What does that do to our blood cells? It blows them up. It floods them. Okay? So the red blood cells swell and eventually burst. So hypotonic would cause our red blood cells to burst.
What hypertonic?
Okay? Which, when it ruptures, is called hemolysis.
So would hypertonic be the one where it shrinks and shrivels?
Hyper.
Yeah.
Yeah, hyper. Yeah. We're getting that next. So hypo,
I am.
swell. I think hypo, hippo. Okay, that's how I remember it because they're really close. Hypo, hippo. Okay? Hypo, hippo. Okay, hypertonic is the opposite. So hyper, they run around, they get skinny, but they end up with spikes. Okay? And it causes cremation of the cell. Okay? So water diffuses out of my red blood cell. That causes this spiky look, and it's called crenation of the cell because it basically forces the red blood cell to collapse upon itself. Okay? So here, the concentration outside is higher than the concentration inside. You sort of got to get this in your head, yes.
So, can I cut myself?
No. Okay? All right, next. Osmotic pressure is the last one, and that's the one I've been talking to you a lot about. Osmotic pressure lets us know which way this is going to dilute. This is what we're going to be doing in lab. So, is it going to move from the dilute to the concentrate to dilute? Do we have a guess of what's going to happen? Are we going to be crenated? Are we going to blow up? What's going to happen? Okay? So we're going to be working with this. If you had a U-tube like this and you put a semi-permeable membrane in between right here, and you put different things on both sides, and you can set this up if you have the right equipment. We're going to do it with just having our membrane be this, and inside and outside. This is dialysis tubes.
This is capital Pi, right?
That is a capital Pi, so that should be written like that. That's a lowercase pi. That's not right. Okay. Notice the introduction here. The one thing I left out earlier, I. I becomes very important. What was I? How many parts is it going to break into? So when we're working with solutions, we're worried about how many particles are there. That's very, very important. So the only difference between Pervner's and the osmotic pressure equation basically is I.
Wait a minute.
Okay, so make sure you add I in there.
And the capital
Capital M is moles divided by volume.
the capital Pi is P.
Capital Pi is P, yes.
What is the osmotic P?
Right.
Okay.
Because now we're dealing with how many particles.
So wait, what's this equation called then?
This is the osmotic pressure equation.
Okay.
But it basically is what? Pervner, the ideal gas equation, we just added I.
And a capital S.
The M is N over V. Okay? All right, so how does this work? This actually is where we work with dialysis. Blood is filtered through the body, through the kidneys, through the process called dialysis. Sometimes kidneys don't work, so we have to do it outside of the body, and people have to come in and get clean that way. In dialysis, water or small molecules or ions can pass through the permeable membrane. But large biological molecules like urea cannot, and so they're able to stop them and clean. That allows the waste products to be removed. So your kidneys are your filters for your body. Okay? If you screw up your kidneys, then you end up on dialysis. Okay?
Quit drinking alcohol.
This is basically what happens. Now, you'll notice right here, stenosis. If you've ever seen that, it is not pretty. I am diabetic, and so usually they take me in when I have to have surgery first thing in the morning. Well, I had one surgery that they didn't do that, and they put me at 5 o'clock at night. And so I hadn't had anything to eat since midnight the night before, and my sugars were really, really low, about 50. And so they decided to give me a glucose solution to up my sugars. The problem was the glucose solution was not isotonic with me. And so what it did is it gave me stenosis of my veins where they pushed it in. Basically, it hardened my arteries where it went in and caused me a lot of problems for that first few weeks until my vein died and they were able to redo stuff. So the same thing happens with people that have to go on dialysis a lot. Because if that solution that they're putting into you is not exactly what it needs to be, it can actually harden the arteries. So this solutions unit, if you're going into medicine, is extremely important. Have the nurse known anything about what she needed to do instead of putting the glucose directly into my IV, should have put it into the solution bag.
You should have told her that.
Well, back then I didn't know head from my tail. About that time when your sugars are 40 to 50, you're almost comatose, so you don't say anything.
Yeah, it's true.
Okay? So make sure, you understand this. This is, if you're going into medical, this unit especially is very important that you understand. Okay? All right. This is what we're going to do. I'm going to show you sort of physically what we're doing. The following mixtures were placed into dialysis bags, like the ones pictured below, like what we're going to be doing. And they're dissolved in pure water. Which of the substances will pass through the bag? So, if I have NaCl and starch, which one will pass through the bag?
NaCl.
NaCl. Think small. Small things will pass through the bag. Big things won't. What about urea?
That'll go.
Urea will.
Not good.
Make that pool water.
Think about the kidneys. What am I trying to stop? What am I trying to filter?
Oh,
Okay? And this is also, neither one of these will go.
so is urea bigger than starch?
Okay? NaCl, or sorry, calcium chloride will. Glucose, that is on the edge. And you'll get to figure that out. I'm not going to tell you the answer to that because you're going to figure that one out in lab.
Wait,
You're actually going to experience that one.
wait, can you say that one more time?
So the smaller the particles of whatever you're trying to pass will pass through. But as you get larger, the dialysis tube will stop it. It'll be like a filter. It'll get caught.
So about how big does it go until it stops?
Okay, so that's what we're going to be looking at in lab. That's what I want to get in your head. What will move through? What won't move through? What will be filtered? Okay, yes.
Kind of stupid question, but
No
is this
stupid.
how people get kidney stones?
Yeah.
Oh, really?
Yeah, because your calcium, if it starts building on each other, starts collecting against with something like a phosphate, it doesn't dissolve. Because phosphates, according to solubility rules, are not soluble, so they start collecting, and now they can't make it through that hole.
Wait, so drinking soda gives you kidney stones?
They can.
Oh.
Okay, so really quickly, refreshing, hypotonic, too much, hippo, gets big, blows up. Okay? Normal, isotonic. Iso meaning same, isotonic. Hyper,
Too much.
shrinks, right? Because if you're hyper, you're going to shrink in volume. And it's shriveled, which is called, who remembers?
Hypertonic.
Hypertonic, but what's it called when it says
Oh,
that?
the
Crenation. Yes. Okay, good job.
What now?
Okay, so colligative property lab. I'm walking you through it real fast. Make sure you're paying attention. Here we go. Because you have to do a bunch of stuff today. So, colligative properties. Who can name all four?
Awesome atomic
Boiling point elevation. I wrote this down.
Vapor pressure lowering. Good. Okay. So, vapor pressure lowering. Freezing point, boiling point elevation, freezing point depression, and osmosis is possible. Okay?
I don't have
All right. So, first thing, you're going to go back in the back, in the very, very back. There is dialysis tubing. You are going to measure out 4 10-centimeter lengths.
Oh, you
4 10-centimeter lengths. 4 10-centimeter lengths. Now, my suggestion to
I
you,
hate myself.
you really need to do this in 2 teams making 1. So there's 4 people in 1 team. Every person is responsible for 1 10-centimeter length. Okay? Everybody got that? So you are responsible for getting you 1 10-centimeter length that you are responsible for. Okay? All right. As a group, you need 4. Okay? You're also going to want to grab little elastics that are the same color for yours. Don't get it the same as anybody else in the group, but decide what color you're going to get for yours so you can keep track of what you have in it.
How many berries do we need?
Okay? So you'll need 1 for each end. Okay? So, first thing you're going to do, 2 people are going to make the sugar. 2 people are going to make the salt. Okay? You got to check it with me. If any one of them is wrong, your whole group gets to go back and redo. Okay? This is what you needed to figure out before you go back and lab. How much do I need to weigh out? So for the part A, you're going to go back. Now, I only have so many 250, so you might get a 100. Okay? Or you have to wait for a 250. In the 250, you're going to weigh out your sample. You're going to put it half full with water. You're going to pour it in. You're going to swirl, swirl, swirl. You're going to fill it up to the line. Okay? Next one. On sugar, this one's going to be a little different. You're not going to use a volumetric class.
That would make more sense.
Yeah.
You're going to use a weigh dish to weigh out the sugar. Okay, watching me, guys. They're going to take pictures later when you're back in lab. Okay, watching me. Okay, you're going to weigh this out. You're going to weigh it into a styrofoam cup. The important thing is that you zero out the styrofoam cup before you start. You're going to weigh that in, put it in. It's going to give a mass. Okay, you're going to add to that mass 250 millimeters total. Okay, so that includes the mass of the solid. You're going to mix that up. Okay, and then you're going to bring me little pieces, and we're going to test each of those. Okay, this is in your lab. Okay, the cuvette you're going to fill 3/4 full. I'm going to test it, see if it's right. If it's right, you go on to the next part, which is check, check. You got to quality check it. You're going to grab your dialysis tubing. Remember I told you got this first up, right? 10 centimeters. You want to put it in distilled water right away because it takes a little while for it to soften up. So put it in distilled water before you make your solutions. Then you're going to come back. You're going to tie one end off. You're going to fill it up with solution. Follow your instructions. The 4 of you need to make all of the things on there. Fill it up, close the other end. You're going to dry it off, pat it off, weigh it. Then you're going to put it in the solution that you need. Okay? And it'll look like this at the end. We're not going to use string, sort of a pain in the butt, but I do have string back there. If the elastics are too hard for you and you want to use string instead, that's fine. Okay? This is what you're going to need to have. Beaker A is going to have salt water. It's going to have a dialysis tube filled with distilled water in it. Beaker B is going to have sugar water with water in the dialysis tube. Beaker C is going to have distilled water outside, sugar water in the dialysis tube. Beaker D, distilled water outside, salt water inside. You need to keep all 4 of those. You need to label each of those beakers with your group's name, and we're going to put them in the hood. Okay? And we'll come back next time and we're going to look at it. That's where you need to get. Also, you need to do a prune. Okay, so you're going to weigh a prune. You're going to put it in water. And then we'll weigh it again when we get back. Okay, so you got 5 beakers. Okay? Everybody know what they're doing? Somewhat? Okay. Be prepared. Let's go.